Welcome back to the Lazy Cosmos, where we make the universe's biggest mysteries surprisingly easy to understand. I'm your host, and today we're diving into a topic that's kept brilliant scientists awake at night for nearly a century. We're talking about Einstein-Rosen bridges, cosmic Swiss cheese, and the possibility that our entire universe might be secretly connected by a vast network of shortcuts through space and time. But here's what's going to blow your mind. The latest research suggests that wormholes might not be hiding in the obvious places like black holes at all. Instead, they could be literally everywhere around us, woven into the very fabric of space-time itself. Think about this for a moment. Every science fiction movie has taught us that if wormholes exist, they must be these massive dramatic portals near black holes or created by advanced alien civilizations. But what if we've been looking in completely the wrong direction? What if nature has been hiding these cosmic highways in plain sight, in places so unexpected that we've spent decades searching for something that's been right under our noses the entire time? Today, we're going to challenge everything you think you know about wormholes, explore the cutting-edge theories that are revolutionizing physics, and discover why some of the smartest people on Earth believe we might be living in a universe that's far more connected than we ever dared to imagine. Imagine a time when our understanding of the universe was on the brink of profound transformation. A time when the boundary between the known and the unknown was about to be shattered. Unknown shifted under the sheer force of a single mind. To set the stage for our journey into wormholes, let's travel back over a century to meet the man who forever altered how we see space, time, and reality itself, Albert Einstein. This towering figure in the pantheon of science was more than the wild-haired genius we recognize from textbooks. He was a relentless explorer of ideas, driven as much by curiosity as by equations. The story of wormholes, and whether they could exist beyond black holes, begins here with Einstein's audacious vision of how the cosmos works. Growing up in late 19th century Germany, young Einstein was fascinated by invisible forces. The sight of a compass needle swinging in the presence of an unseen magnetic field sparked his imagination. What if the universe itself was governed by hidden rules, waiting to be revealed? This early curiosity ultimately led Einstein to topple the classical notions of Newtonian physics, which had dominated the scientific landscape for centuries. Newton's universe was predictable, mechanical, tick-tock, like pieces moving on a grand celestial chessboard. But Einstein sensed that reality was deeper, more mysterious. In 1905, he published his theory of special relativity, shaking the foundations of science by arguing that space and time were not separate entities, but interwoven into a single continuum, space-time. The implications were staggering. Suddenly, time was not absolute, and distances in space could shrink or stretch depending on how fast you moved. Einstein's equations described how the speed of light was the same for all observers, no matter how fast they traveled. That alone was enough to make physicists across the globe sit up and take notice. But Einstein was not done. He saw farther than anyone else. 10 years later, in 1915, he released his masterpiece, The General Theory of Relativity. Here, Einstein proposed that gravity was not a mysterious force transmitted between masses, as Newton believed, but a result of the curvature of space-time itself. Picture the cosmos as a giant rubber sheet. When you place a massive object, say, the sun, on this sheet, it warps the surface, creating dips and valleys. Smaller objects, like planets, roll around these curves, following the paths carved by gravity. This geometric vision of gravity forever changed our view of the universe, and it planted the seeds for the story we're unraveling today. But Einstein was never satisfied with simple answers. He kept asking deeper questions. If space and time can bend, are there shortcuts through the universe's fabric itself? Could there be hidden passageways, tunnels, or bridges that connect distant points, providing cosmic detours no one had ever imagined? These questions remained speculative for decades, yet there was a tantalizing hint in the mathematics. Fast forward to the 1930s. The world is in turmoil, but in Princeton, New Jersey, Einstein is at work alongside Nathan Rosen, another sharp mind drawn to the mysteries of relativity. Together, they revisit Einstein's equations and uncover something extraordinary. Their calculations reveal that, under certain conditions, the geometry of spacetime allows for a peculiar structure, the Einstein-Rosen bridge. So, what is an Einstein-Rosen bridge? Let's break down the concept in a way anyone can grasp. Imagine taking a sheet of paper and marking two dots at opposite ends. Normally, if you wanted to draw a line between the dots, you'd have to trace across the paper, traveling its length. But what if you folded the paper so the dots touched? Suddenly, what was once a long journey becomes instant, a shortcut through the paper itself. This is the essence of an Einstein-Rosen bridge, a theoretical tunnel connecting two separate regions of spacetime. Einstein and Rosen's bridge wasn't just a mathematical artifact. It posed a mind-bending possibility. Could such a tunnel actually exist in nature, allowing objects, or perhaps information, to travel from one part of the universe to another without following the normal, lengthier path through space? This concept would later be popularly known as a wormhole, an evocative term coined by physicist John Wheeler decades after Einstein's original work. The reasoning is simple and brilliant. Just as a worm burrows through an apple, creating a tunnel that connects two points on the surface, a wormhole is a tunnel through the universe's very fabric. Now, here's where the plot thickens. Einstein and Rosen built their bridge out of the solutions to the equations of general relativity. Their discussions were not idle dreaming, but rigorous mathematical exploration. The bridge connected two black holes, regions where gravity is so intense that nothing, not even light, can escape. Yet in reality, even these mathematical bridges posed a problem. They were unstable. If something tried to traverse the tunnel, the bridge would collapse faster than you could say space-time, snapping shut like a trap. As dazzling as the idea was, Einstein and Rosen saw their bridge less as a cosmic highway and more as a mathematical curiosity, a way to avoid the troubling singularities at the hearts of black holes. But scientific history is filled with moments when mathematical curiosities turn into revolutionary breakthroughs. Consider, for example, the story of imaginary numbers in mathematics. Once dismissed as pointless abstractions, now essential in fields as diverse as engineering, electrical theory, and quantum physics. Similarly, the Einstein-Rosen bridge lingered for decades in the background, seemingly impossible to realize, until new thinkers came along and asked, "What if?" This brings us to the interplay between imagination and rigor that defines scientific progress. In college classrooms and informal discussions, the concept of wormholes began to slip from pure math into the realm of speculative science fiction. Writers and filmmakers seized upon Einstein's bridge, using it as a gateway to distant planets, alternative universes, and wild adventures. But real physicists, too, started pondering what conditions, if any, could possibly allow a wormhole to be stable. Consider the relentless curiosity of theoretical physicists throughout the mid-20th century. In the decades following Einstein's death in 1955, researchers continued exploring the strange geometry of space-time. They found that solutions to Einstein's equations could, under extremely exotic circumstances, describe wormholes that might allow not only travel across space, but potentially through time as well. The connection between wormholes and time travel, once the stuff of pure fantasy, traced back to Einstein's deep insights about the flexibility of space-time itself. Now let's pause for a moment and ask ourselves, why did Einstein pursue these questions so passionately? What made him so adept at thinking beyond the boundaries of ordinary science? Part of the answer lies in his willingness to question assumptions. Where others saw unbreakable rules, Einstein saw opportunities for innovation. When the rest of the world was fixated on tangible, measurable phenomena, he remained curious about the very structure of reality. His correspondence and lectures from the 1930s and 1940s reveal a mind that never rested. He wondered about singularities, horizons, and the deep paradoxes lurking underground in his own theories. Einstein realized that the universe was not a static canvas, but a living, unfolding drama, a place where space and time themselves were actors on the cosmic stage. For Einstein, mathematics was more than numbers and symbols. It was a language of nature, conveying possibilities that had yet to be fully understood. The legacy of this thinking can hardly be overstated. Not only did Einstein's work inspire generations of physicists to grapple with the wildest ideas, but it fundamentally altered our metaphysical sense of place. Before Einstein, the cosmos was described in terms too simple, too deterministic. After Einstein, nothing was ever quite as it seemed. Space and time had texture, curvature, and a secret capacity for surprises. Let's return to the question at the heart of this video, and to the channel, the lazy cosmos. If wormholes are a feature of Einstein's equations, how do we begin to search for them in reality? What signs, what clues, might tell us they exist beyond black holes? During Einstein's lifetime, the tools of astronomy were crude by modern standards. Telescopes scanned the light of stars, but could not parse the profound structure of space-time. And yet, Einstein's predictions about gravity waves and cosmic curvature set the stage for discoveries that would come long after his passing. Through the 20th and 21st centuries, scientists built ever more precise instruments, radio telescopes, X-ray detectors, and gravitational wave observatories. Einstein's equations continued to yield new insights. The detection of gravitational waves in 2015, using the LIGO observatory, proved a prediction he had made a century earlier. These ripples in the fabric of space-time confirmed, yet again, how accurate Einstein's mathematical vision had been. And they opened the door to even greater mysteries. Could these waves, under certain conditions, reveal the presence of wormholes? Could we someday detect the telltale signature of an Einstein-Rosen bridge in the signals from space? In all these explorations, Einstein's method remains as vital as his conclusions. He combined intuition with skepticism, never rushing to believe in what couldn't be observed, but always pursuing the implications of his own ideas to their logical ends. This balance of openness and rigor remains the gold standard in physics today. Here's something fascinating to ponder. What if Einstein's original bridges weren't just theoretical curiosities, but the early sketches of phenomena we have yet to observe? Modern physicists use the language of non-traversable and traversable wormholes, debating under what circumstances the latter might actually exist. Some imagine vast cosmic tunnels stabilized by exotic matter, substances with properties unlike any you or I will encounter in daily life. Others explore the quantum realm, where the foam of space-time might be riddled with baby wormholes, so tiny and fleeting they escape our detection. The universe, it turns out, may be far stranger than anyone, including Einstein, ever dreamed. Black holes are not just gravitational traps, but perhaps cosmic laboratories where space-time comes unglued from ordinary rules. Near their horizons, the fabric twists and warps to such extremes that all bets are off. If an Einstein-Rosen bridge could form and somehow remain open, our concepts of travel, causality, and even identity would change overnight. And yet, let's remember Einstein's fundamental humility. He was wise enough to admit that nature often keeps her secrets long after humans have drawn their equations. "Subtle is the Lord," he famously said, "but malicious he is not." In other words, the universe may hide its deepest truths for a time, but it does so not out of spite, but out of a complexity we have yet to fully grasp. Science, at its core, is a conversation with the unknown. Einstein's work invites us into that dialogue, not only to solve practical problems, but to wonder, speculate, and dream. By tracing the evolution of the Einstein-Rosen bridge, we encounter a story that is as much about philosophical curiosity as mathematical precision. It's about bravery, the willingness to confront ideas too strange for conventional wisdom. Before we move on to what comes after Einstein, the quest to discover wormholes beyond black holes, let's reflect on what this section reveals about our place in the cosmos. The boundaries of reality may not be fixed. The shortcuts may already be there, waiting for discovery. The challenge, as Einstein showed, is not simply to see what's obvious, but to ask what the universe permits when we fold our thinking in unconventional ways. Einstein's connection to the wormhole story is more than academic. It is the spark, the ignition, behind all our curiosity today. It reminds us that science isn't a catalog of answers. It's a quest for questions with answers that sometimes reshape everything we know. As we continue our journey on the lazy cosmos, keep in mind the power of a single question. What do we find when we search for bridges in the universe? The answer may change not just how we travel through space, but how we imagine what's truly possible. Wormholes are not just a theoretical what if. They are a legacy of Einstein's creative and mathematical wonder. In his connection to this mystery, we find both the roots of the scientific adventure and a glimpse of the vast interconnected universe that may yet unfold before us. And as we transition to the next chapter of our story, carry this spirit of curiosity with you. The idea that sometimes bending our perspective is the shortest route to extraordinary discovery. Now that we've explored Einstein's revolutionary bridge through space-time, let's dive into the next chapter of our cosmic mystery. For decades after Einstein and Rosen first described their theoretical tunnel, scientists found themselves fixated on one particular question. If these wormholes could actually exist in our universe, where would nature hide them? The answer seemed almost obvious to the brilliant minds of the mid-20th century. If you're looking for the most extreme distortions of space-time, the places where Einstein's equations reach their most dramatic conclusions, there's really only one cosmic phenomenon that fits the bill: black holes. These gravitational monsters became the natural suspects in the hunt for wormholes, and for very good reason. Think about what a black hole actually represents in the fabric of our universe. Picture space-time as that rubber sheet we mentioned earlier, stretched taut across the cosmos. Now imagine dropping not just a bowling ball, but something infinitely dense onto that sheet. The result isn't just a gentle dip. It's a puncture so severe that the sheet curves back on itself, creating what physicists call an event horizon. This is the point of no return, the boundary beyond which nothing, not matter, not energy, not even light itself, can escape the black hole's gravitational embrace. It's as if the universe has developed a cosmic drain, pulling everything nearby into an inescapable spiral toward the center. But here's where the story becomes truly fascinating for wormhole hunters. The mathematics that describe black holes are intimately connected to the same equations that gave birth to Einstein-Rosen bridges. In fact, the original formulation of these bridges required two black holes as their endpoints. It was as if nature was telling us that these cosmic vacuum cleaners weren't just endpoints for matter and energy. They might actually be gateways to somewhere else entirely. The idea was seductive in its elegance. Perhaps every black hole in our universe was connected to another black hole somewhere else, creating a vast network of cosmic tunnels spanning the depths of space. This connection between black holes and wormholes wasn't just mathematical poetry. It had serious theoretical backing. When physicists examined the geometry of space-time around black holes, they discovered something remarkable. The extreme curvature didn't just bend space and time. Under certain conditions, it could theoretically create a bridge to another region of space-time entirely. Imagine the black hole not as a cosmic dead end, but as one mouth of a tunnel whose other end might emerge as what we call a white hole, a theoretical object that spews matter and energy outward, the exact opposite of its black counterpart. The implications were staggering to contemplate. If this were true, then the matter falling into a black hole wouldn't simply disappear into some unknowable singularity. Instead, it would travel through this cosmic tunnel and emerge somewhere else in the universe, possibly in a completely different galaxy, or even in a different universe altogether. The black holes scattered throughout our cosmos, and we know there are millions of them, perhaps billions, wouldn't just be gravitational monsters devouring everything in their path. They would be the universe's own transportation system, a network of cosmic highways connecting distant regions of space and time. But as scientists delved deeper into this possibility, they encountered a fundamental problem that seemed to dash their hopes for cosmic travel. The issue wasn't with the mathematics. Einstein's equations clearly allowed for these bridges. The problem was with physics itself, specifically the behavior of spacetime near the black hole's event horizon. As you approach a black hole, the gravitational field doesn't just grow stronger. It grows stronger at an accelerating rate. Your feet, being slightly closer to the black hole than your head, would experience significantly more gravitational pull. This difference in gravitational force across your body creates what physicists have dubbed spaghettification. The term might sound amusing, but the reality is anything but funny. Long before you could explore any hypothetical wormhole tunnel, the The tidal forces near the black hole would stretch your body like a piece of taffy being pulled in a candy machine. Your atoms would be torn apart, your very molecular structure unraveled by forces so intense they defy comprehension. Even if a wormhole existed within the black hole, even if there were a cosmic highway waiting to transport you across the universe, you'd never survive the journey to reach it. You'd be reduced to a stream of subatomic particles long before you could step through any interdimensional doorway. This realization led to what many scientists considered the black hole wormhole paradox. The very places where wormholes seemed most likely to exist, where space-time curvature reached its most extreme values, were precisely the places where they would be most impossible to use. It was like discovering the entrance to a magical kingdom, only to find it guarded by an insurmountable wall of fire. The mathematics promised cosmic shortcuts, but the physics seemed to make them forever inaccessible to any form of life or intelligence that might want to use them. But the story doesn't end there, because some of the most brilliant minds in physics refused to accept this apparent dead end. Throughout the 1970s and 1980s, researchers began asking more nuanced questions about the relationship between black holes and wormholes. What if the connection wasn't as straightforward as they had initially imagined? What if the extreme conditions near black holes weren't just obstacles to wormhole travel, but actually clues about where to look for more accessible cosmic tunnels? This line of thinking led to a fascinating shift in perspective. Instead of seeing black holes as the destinations for wormhole hunting, some scientists began to view them as laboratories for understanding the fundamental nature of space-time itself. The incredible density and gravitational fields near black holes create conditions that exist nowhere else in the observable universe. In these extreme environments, the normal rules of physics stretch to their breaking points, potentially revealing phenomena that remain hidden under ordinary circumstances. Consider, for example, what happens at the very center of a black hole, the singularity. Here, according to our current understanding, matter is compressed to infinite density and space-time curvature becomes infinite. But infinity is a red flag in physics, usually indicating that our theories have reached their limits. Many scientists suspect that before you actually reach the mathematical singularity, quantum effects that we don't yet fully understand would take over, potentially creating conditions far stranger than anything classical physics predicts. This is where the story takes an unexpected turn. Some theoretical physicists have proposed that the extreme quantum conditions at the heart of a black hole might not lead to a simple point of infinite density, but to something far more exotic, a quantum bounce that connects to another region of space-time. In this scenario, the black hole becomes not just a gravitational prison, but a cosmic transformation chamber where matter and energy are quantum mechanically transported to distant locations. But perhaps even more intriguing is the possibility that black holes might be teaching us about wormholes indirectly by showing us the kinds of extreme conditions necessary for space-time to develop these cosmic shortcuts. The immense gravitational fields near black holes demonstrate that space and time are far more flexible than our everyday experience suggests. If space-time can be curved so dramatically by mass and energy, if it can be stretched and compressed to such extreme degrees, then perhaps other phenomena in the universe could create similar distortions under different circumstances. This realization opened up entirely new avenues of investigation. Scientists began to wonder, What other cosmic phenomena might generate the kinds of space-time distortions necessary for wormhole formation? What if black holes weren't the only places in the universe where the fabric of reality became flexible enough to support these cosmic tunnels? What if we had been looking in the most obvious place, but not necessarily the most promising one? The black hole connection also taught researchers something crucial about the nature of wormholes themselves. If these cosmic shortcuts were going to be useful for anything, whether for travel, communication, or simply expanding our understanding of the universe, they would need to be stable. The theoretical wormholes connected to black holes suffered from a fatal flaw. They were inherently unstable, collapsing faster than anything could traverse them. This instability wasn't just a technical hurdle, it was a fundamental feature of how these particular space-time geometries behaved. But instability in one context doesn't mean impossibility in all contexts. The lessons learned from studying black hole-related wormholes provided crucial insights into what would be required to create or find stable versions of these cosmic tunnels. Scientists realized they would need to look for environments where space-time could be curved dramatically, but in a more controlled and sustainable way than the chaotic conditions near black holes. This search for stability led to some of the most exotic theoretical proposals in all of physics. Researchers began investigating the possibility that stable wormholes might require forms of matter and energy unlike anything we observe in ordinary circumstances. They spoke of exotic matter with negative energy density, substances that would push space-time apart rather than pulling it together, essentially acting as cosmic struts to hold wormhole tunnels open against their natural tendency to collapse. The black hole connection also revealed something profound about the relationship between different areas of physics. The study of wormholes couldn't be separated from the study of quantum mechanics, thermodynamics, and information theory. Black holes, it turns out, are not just gravitational phenomena. They're quantum objects with temperature, entropy, and information content. This realization suggested that any complete understanding of wormholes would need to bridge the gap between Einstein's classical description of gravity and the quantum mechanical description of matter and energy. As we stand today, the black hole connection remains one of the most important chapters in the wormhole story. These gravitational giants taught us that space-time is far more dynamic and flexible than we once imagined. They showed us the kinds of extreme conditions where the normal rules of physics break down, potentially creating opportunities for phenomena we never expected. Most importantly, they demonstrated that while the obvious answer isn't always the right answer, it can still provide crucial clues for finding the truth. The legacy of the black hole connection extends far beyond the specific question of whether wormholes exist near these cosmic monsters. It represents a fundamental shift in how we think about the universe itself. Instead of seeing space and time as fixed stages on which cosmic drama unfolds, we now understand them as active participants in that drama, capable of bending, stretching, and potentially even developing shortcuts that connect distant regions of reality. But perhaps the most important lesson from the black hole connection is this: when nature seems to close one door, it often opens another. The apparent impossibility of using black hole wormholes for travel didn't end the search for cosmic shortcuts. It redirected that search toward more promising territories. It forced scientists to think more creatively about where and how wormholes might exist in forms that could actually be detected, studied, and potentially even utilized. As we prepare to move beyond the black hole connection and explore the truly revolutionary ideas about where wormholes might actually exist, remember this: sometimes the most important scientific discoveries come not from finding what we expect, but from understanding why our expectations were wrong. The black holes taught us that wormholes are possible, but they also taught us to look beyond the obvious. They prepared us to consider possibilities so strange and unexpected that they challenge our most basic assumptions about the nature of reality itself. The cosmic monsters that first seemed like the natural homes for wormholes have instead become our teachers, showing us that the universe is far stranger, far more connected, and far more full of possibilities than we ever dared to imagine. And that realization is about to take us on a journey to places in the cosmos where wormholes might not just be mathematical curiosities, but actual features of the universe waiting to be discovered. Here we are, at the crossroads of cosmic discovery, where conventional wisdom meets revolutionary thinking, and where the universe reveals its most closely guarded secrets. After decades of fixating on black holes as the natural homes for wormholes, something remarkable happened in the world of theoretical physics. Scientists began to realize that they might have been searching in the most dramatic place, but not necessarily the most promising one. It's a classic example of what researchers call streetlight bias, looking for your lost keys under the lamppost, not because that's where you dropped them, but because that's where the light is brightest. Black holes provided the most obvious extreme conditions for space-time distortion. But what if the universe was hiding its cosmic shortcuts in places far more subtle, far more unexpected, and ultimately far more accessible? This shift in thinking didn't happen overnight. It required a fundamental reimagining of what wormholes could be and where they might exist. The breakthrough came when physicists began to consider the quantum nature of space-time itself. You see, when Einstein first conceived of his geometric vision of gravity, he was working with what we call classical physics, a world where space and time formed a smooth, continuous fabric. But as quantum mechanics developed throughout the 20th century, scientists discovered that at the smallest scales of reality, nothing is smooth or continuous. Everything, including space-time itself, becomes grainy, foamy, and probabilistic. Enter one of the most brilliant minds to tackle this problem. Kip Thorne, the Nobel Prize-winning physicist who would later become famous for his consulting work on the movie Interstellar. But long before Hollywood came calling, Thorne was asking questions that would revolutionize our understanding of wormholes. In the 1980s, he began exploring a deceptively simple question. What if wormholes didn't need to be connected to black holes at all? What if the extreme curvature of space-time could be achieved through entirely different means? What if we had been thinking about this problem completely backwards? Thorne's approach was characteristically elegant and mathematically rigorous. Instead of starting with black holes and trying to find wormholes within them, he started with the desired outcome, a stable, traversable wormhole, and worked backwards to determine what conditions would be necessary to create such a thing. This reverse engineering approach led to some of the most exotic and mind-bending concepts in all of physics. But before we dive into those concepts, let's take a moment to appreciate just how radical this shift in thinking really was. Imagine you've spent your entire career as an explorer, convinced that the greatest treasures must be hidden in the most dangerous and inaccessible places, at the bottom of the deepest ocean trenches or atop the highest mountain peaks. Then someone comes along and suggests that the real treasures might be buried in your own backyard, in places so ordinary and unremarkable that you've walked past them thousands of times without a second thought. That's essentially what happened in wormhole physics during the 1980s and 1990s. Scientists began to realize that the cosmic shortcuts they sought might not require the extreme drama of black holes, but could potentially exist in environments that were exotic in entirely different ways. One of the most revolutionary ideas to emerge from this period was the concept of microscopic wormholes existing in what physicists call the quantum foam of spacetime. To understand this concept, we need to zoom in on reality to scales so small that they make atoms look like galaxies. At distances around the Planck length, about 10 to the negative 35th meters, which is unimaginably tiny, the smooth geometry of Einstein's spacetime breaks down completely. At this scale, space and time don't form a continuous fabric, but rather a seething, bubbling foam of quantum fluctuations. In this quantum foam, virtual particles pop in and out of existence, energy fluctuates wildly, and the very geometry of space-time becomes uncertain. It's a realm where the normal rules of cause and effect become fuzzy, where the distinction between here and there loses much of its meaning. And according to some of the most advanced theories in physics, this quantum foam might be absolutely riddled with tiny wormholes, microscopic tunnels through space-time that appear and disappear in time frames so brief that they exist for less than the time it takes light to travel the width of a proton. Now, you might be thinking, what good are wormholes so small and short-lived that they're essentially undetectable? But here's where the story takes its most exciting turn. Some physicists have proposed that these quantum wormholes might not be the dead end they initially appear to be. Under the right conditions, with the right kind of exotic matter or energy, these microscopic tunnels could potentially be stretched, stabilized, and expanded into macroscopic cosmic highways. Think of it like this. Imagine you're walking through a forest and you notice tiny rabbit trails crisscrossing through the underbrush. These trails are too small for humans to use, but they reveal something important about the landscape. They show you where natural pathways exist, where the terrain is most conducive to movement. With the right tools and enough effort, you could potentially widen these rabbit trails into hiking paths and eventually into full-sized roads. The quantum wormholes in spacetime's foam might be similar, natural pathways that, with sufficient understanding and technology, could be developed into something far more substantial. But the quantum foam isn't the only place where researchers began looking for wormholes beyond black holes. Another revolutionary idea emerged from the study of cosmic strings, theoretical objects that might have formed in the earliest moments after the Big Bang. These strings, if they exist, would be incredibly thin, but potentially trillions of miles long, stretching across vast regions of space. More importantly for our story, cosmic strings would be incredibly dense, creating significant distortions in space-time wherever they exist. The mathematics describing cosmic strings revealed something fascinating. Where two cosmic strings intersect or come close to each other, they could potentially create the kind of space-time geometry necessary for wormhole formation. Unlike the chaotic, destructive environment near black holes, the regions around cosmic string intersections might provide a more controlled environment for stable wormhole development. These wouldn't be the violent, short-lived tunnels connected to gravitational monsters, but potentially calm, stable passages through space-time that could persist for cosmic ages. Even more intriguingly, some theoretical work suggested that cosmic strings might not just create wormholes incidentally, but that they might actually be wormholes themselves, or at least contain wormhole-like properties. In this scenario, traveling along a cosmic string wouldn't just take you through normal space. It might take you through shortcuts in space-time itself, allowing for faster-than-light travel without actually exceeding the speed of light locally. The exploration of possibilities beyond black holes also led scientists to consider the role of dark energy and dark matter in wormhole formation. These mysterious components make up about 95% of our universe, yet we understand them so poorly that we can barely detect them, let alone predict their behavior. But some researchers have proposed that the very properties that make dark energy and dark matter so elusive might also make them ideal candidates for supporting wormhole structures. Dark energy, in particular, has properties that seem almost tailor-made for wormhole physics. Unlike ordinary matter and energy, which create attractive gravitational effects, dark energy appears to have a repulsive effect, pushing space apart and driving the accelerating expansion of the universe. This repulsive nature is remarkably similar to the exotic matter that theoretical physicists determined would be necessary to keep wormholes stable and traversable. Could it be that dark energy isn't just some mysterious cosmic phenomenon, but actually the natural mechanism by which the universe maintains a network of stable wormholes? The implications of this possibility are staggering. If dark energy does play a role in wormhole formation and stability, then wormholes wouldn't be rare cosmic curiosities confined to the neighborhoods of black holes. They would be woven throughout the entire universe, supported by the same force that's driving cosmic expansion. Every cubic meter of seemingly empty space might contain traces of the exotic energy necessary to support microscopic wormhole networks. This line of thinking also opened up entirely new possibilities for wormhole detection and study. Instead of waiting for the technology to observe the extreme environments near black holes, scientists began developing theories about how wormhole networks might leave detectable signatures in the cosmic microwave background radiation, in the distribution of galaxies, or in the subtle patterns of dark energy fluctuations throughout the universe. Perhaps even more exciting, some researchers began to propose that certain astronomical phenomena we've already observed might actually be evidence of wormhole activity. Fast radio bursts, brief, intense flashes of radio waves from distant galaxies, have puzzled astronomers since their discovery. While most explanations involve neutron stars or other conventional astrophysical objects, a few researchers have suggested that these bursts might be the signature of information or energy passing through cosmic wormhole networks. The shift away from black holes as the exclusive homes for wormholes also forced scientists to reconsider the relationship between wormholes and quantum mechanics. In the quantum world, particles can exhibit what Einstein famously called spooky action at a distance, quantum entanglement, where particles remain mysteriously connected regardless of the distance separating them. Some of the most cutting-edge research in physics has begun to explore whether quantum entanglement and wormholes might be different aspects of the same underlying phenomenon. This quantum connection to wormholes suggests possibilities that are almost too strange to contemplate. If quantum entanglement and wormholes are related, then every quantum measurement, every quantum interaction happening around us might be mediated by microscopic wormhole connections. The quantum world that underlies all of reality might literally be held together by an invisible network of space-time shortcuts, making the universe far more interconnected at a fundamental level than we ever imagined. The exploration beyond obvious answers also revealed something profound about the nature of scientific discovery itself. For decades, the obvious answer, that wormholes would be found near black holes, dominated research and speculation. But the most revolutionary insights came when scientists were brave enough to question their assumptions, to look beyond the most dramatic and obvious possibilities, and to consider scenarios that seemed almost boringly mundane by comparison. This pattern repeats throughout the history of science. The most important discoveries often come not from studying the most extreme or obvious examples of a phenomenon, but from understanding its subtle, hidden manifestations. DNA wasn't discovered by studying the most complex life forms, but by examining simple bacteria and viruses. Quantum mechanics wasn't revealed by studying the largest objects in the universe, but by investigating the behavior of individual atoms and photons. The lesson for wormhole research is clear. If these cosmic shortcuts exist, they're probably not hiding in the most dramatic places we can imagine. They're more likely to be woven into the everyday fabric of space-time, existing at scales and in environments where we haven't thought to look, maintained by forces and phenomena that we encounter every day, but don't fully understand. As we stand at the threshold of even more revolutionary ideas about where wormholes might exist, remember this: the universe has a history of hiding its greatest secrets in plain sight. The most profound truths about reality often emerge not when we look at the most extreme examples of cosmic phenomena, but when we learn to see the extraordinary in the ordinary, the cosmic in the quantum, and the impossible in the everyday fabric of existence itself. The journey beyond the obvious has shown us that wormholes, if they exist, are probably far stranger, far more subtle, and far more ubiquitous than we ever dared to imagine. And that realization is about to take us to places in our understanding of the universe that will challenge every assumption we've ever made about the nature of space, time, and reality itself. Now, we arrive at what many physicists consider the ultimate roadblock in the quest for wormholes, a problem so fundamental and seemingly insurmountable that it has consumed the careers of brilliant researchers for decades. As scientists began to seriously explore the mathematics of stable, traversable wormholes, they discovered something that sounds like it belongs in the realm of pure fantasy. To create and maintain these cosmic shortcuts, you would need a form of matter unlike anything that has ever been observed in our universe. This isn't just about finding rare elements or exotic particles. We're talking about something that violates our most basic understanding of how matter and energy behave. Welcome to the world of exotic matter, where the very foundations of physics bend in ways that challenge everything we thought we knew about reality. To understand just how bizarre exotic matter truly is, let's start with something fundamental about the universe around us. Every single thing you've ever encountered, every atom in your body, every molecule of air you breathe, every particle of light that reaches your eyes, has what physicists call positive energy density. This means that all ordinary matter and energy contribute to the curvature of space-time in a way that creates attractive gravitational effects. When Einstein described how mass and energy warp the fabric of spacetime, he was describing this positive energy density property. It's so fundamental to our experience of reality that we rarely even think about it, yet it governs everything from why objects fall toward Earth to why galaxies hold together across cosmic distances. But here's where the wormhole problem becomes truly mind-bending. When physicists worked out the detailed mathematics of what would be required to keep a wormhole open and stable, they discovered that you would need matter with negative energy density, matter that pushes space-time apart rather than pulling it together. This isn't just a minor technical detail. It's a complete reversal of how we understand matter and energy to behave. Imagine if gravity suddenly started pushing objects away from massive bodies instead of pulling them in. That's the level of strangeness we're dealing with when we talk about exotic matter. The term exotic matter itself can be misleading because it suggests that we're simply talking about some unusual type of ordinary matter, like a rare isotope or an unstable particle. But exotic matter is far stranger than that. It represents a fundamental violation of what physicists call the weak energy condition, one of the most basic assumptions about how energy behaves in our universe. According to this condition, energy density should always be positive when measured by any observer moving through spacetime. Exotic matter throws this assumption out the window, requiring energy densities that are not just zero, but actually negative. To grasp just how revolutionary this concept is, consider what negative energy density would mean in practical terms. If you could somehow create a region of space filled with exotic matter, objects near that region would experience gravitational repulsion rather than attraction. Instead of falling toward the exotic matter, they would be pushed away from it. Light passing through or near such a region wouldn't be bent inward as it is near ordinary massive objects. It would be bent outward, creating gravitational lensing effects that are the exact opposite of what we observe around stars, galaxies, and black holes. The mathematical requirements for wormhole stability make the exotic matter problem even more challenging. It's not enough to simply have negative energy density. You need specific types and distributions of this impossible matter to create what physicists call a traversable wormhole. The exotic matter must be arranged in precisely the right configuration around the wormhole throat, creating a kind of cosmic scaffolding that prevents the tunnel from collapsing under its own gravitational influence. Think of it as trying to keep a soap bubble from popping, except that the forces trying to collapse your bubble are among the most powerful in the universe. The amount of exotic matter required is another staggering challenge. Even for a relatively small wormhole, perhaps large enough for a spacecraft to pass through, the calculations suggest you would need quantities of negative energy matter comparable to the mass of entire stars. For larger, more stable wormholes that could accommodate significant traffic or remain open for extended periods, the exotic matter requirements scale up to truly astronomical proportions. We're talking about manipulating amounts of impossible matter that dwarf the total mass energy content of entire solar systems. But perhaps the most troubling aspect of the exotic matter problem is that it seems to violate fundamental principles that govern the stability of space-time itself. The mathematical framework that describes our universe includes several energy conditions that prevent various types of pathological behavior. These conditions ensure that space-time remains stable, that causality is preserved, and that the universe doesn't develop paradoxes or inconsistencies that would make physics impossible. Exotic matter, by its very definition, violates these protective principles. The violation of energy conditions opens up a Pandora's box of potential problems. If exotic matter can exist in the quantities and configurations required for wormholes, then the same principles that allow wormholes might also allow for closed time-like curves, paths through space-time that loop back on themselves, potentially enabling time travel to the past. While time travel might sound exciting, it creates logical paradoxes that could fundamentally undermine the consistency of physical law. The grandfather paradox, the possibility of traveling back in time and preventing your own birth, is just one example of the kinds of logical contradictions that exotic matter might enable. These theoretical problems led many physicists to embrace what became known as the chronology protection conjecture, proposed by Stephen Hawking. According to this idea, the laws of physics would somehow conspire to prevent the formation of exotic matter in the quantities and configurations necessary for time travel or large-scale wormhole construction. The universe, in Hawking's view, protects itself against paradoxes by making the required exotic matter physically impossible to create or maintain. However, the story of exotic matter isn't entirely one of impossibility and violation. Some researchers have discovered that certain quantum mechanical effects can, under very specific and limited circumstances, create regions of negative energy density. The most famous example is the Casimir effect, discovered by Dutch physicist Hendrik Casimir in 1948. When two perfectly conducting metal plates are placed extremely close together in a vacuum, quantum fluctuations in the electromagnetic field create a tiny attractive force between the plates. This force arises because the space between the plates contains less energy than the surrounding vacuum, a form of negative energy density. The Casimir effect proves that negative energy density isn't just a mathematical abstraction. It's a real, measurable phenomenon that has been confirmed in numerous laboratory experiments. The effect is incredibly small, producing forces measured in nanonewtons over areas of square centimeters. But it demonstrates that the quantum vacuum can indeed exhibit the exotic properties required for wormhole physics. This discovery gave hope to researchers who had begun to suspect that exotic matter might be forever beyond the reach of physical reality. But while the Casimir effect shows that negative energy density is possible, it also reveals just how challenging the exotic matter problem truly is. The amount of negative energy produced by even the most optimized Casimir configurations is utterly negligible compared to what would be required for macroscopic wormholes. To create enough exotic matter for even the smallest traversable wormhole, you would need to scale up the Casimir effect by factors of trillions upon trillions, a technological challenge that seems to approach the impossible. Some theoretical physicists have proposed more exotic quantum mechanical scenarios that might produce larger quantities of negative energy. These include quantum field configurations in curved spacetime, vacuum polarization effects near rotating black holes, and various speculative quantum phenomena that might occur in the early universe or in regions of extreme gravitational field strength. Each of these scenarios pushes the boundaries of our understanding of quantum mechanics and general relativity, exploring regimes where our current theories might be incomplete or incorrect. The search for naturally occurring exotic matter has led researchers to some of the most extreme environments in the known universe. Near the event horizons of rotating black holes, quantum effects can create regions where energy density becomes negative relative to certain observers. The intense electromagnetic fields around neutron stars might create quantum vacuum polarization effects that produce exotic matter-like conditions. Even the expansion of the universe itself, driven by dark energy, creates scenarios where space-time exhibits some properties similar to those required for wormhole stabilization. Dark energy, in particular, has captured the attention of researchers studying the exotic matter problem. This mysterious component of our universe, which makes up roughly 68% of the total mass energy content, exhibits properties that are remarkably similar to exotic matter. Dark energy has negative pressure and drives the accelerating expansion of space itself, suggesting that it might represent a form of naturally occurring exotic matter that permeates the entire cosmos. If dark energy could be concentrated, controlled, or manipulated in the right ways, it might provide a solution to the exotic matter problem that doesn't require violating fundamental physical principles. Some researchers have proposed that advanced civilizations might develop technologies capable of harvesting dark energy or creating artificial dark energy-like fields that could support wormhole construction. These ideas remain highly speculative, but they represent potential pathways around the exotic matter roadblock that don't require abandoning the laws of physics entirely. The exotic matter problem also intersects with some of the deepest questions in quantum mechanics and cosmology. The quantum vacuum, the lowest energy state of quantum fields, is far from empty, filled with virtual particle pairs that constantly appear and disappear. Some theorists have suggested that the vacuum itself might contain the seeds of exotic matter, requiring only the right kind of manipulation or organization to reveal negative energy densities on macroscopic scales. String theory and other advanced theoretical frameworks have also contributed to discussions of exotic matter. In some versions of string theory, the extraspatial dimensions beyond our familiar three could harbor forms of matter and energy, with properties unlike anything in our ordinary experience. These bulk effects from higher dimensions might provide natural sources of exotic matter or offer alternative mechanisms for creating wormhole-like shortcuts through space-time that don't require traditional exotic matter at all. The practical implications of the exotic matter problem extend far beyond theoretical physics. If exotic matter could somehow be created, controlled, and maintained in sufficient quantities, it wouldn't just enable wormhole construction. It would revolutionize our understanding of energy, propulsion, and space-time engineering. Anti-gravity devices, faster-than-light communication systems, and revolutionary new forms of energy generation might all become possible in a universe where exotic matter could be harnessed. But the exotic matter problem also serves as a profound reminder of the limitations of our current understanding. Despite centuries of scientific progress, despite our ability to peer billions of light years into space and probe the behavior of subatomic particles, we still encounter phenomena that challenge our most fundamental assumptions about reality. Exotic matter represents one of these challenges, a requirement so strange and seemingly impossible that it forces us to question whether our theories are complete or whether nature has tricks up her sleeve that we haven't yet discovered. As we prepare to explore even more mind-bending possibilities about where and how wormholes might exist, remember that the exotic matter problem isn't necessarily a dead end. Throughout the history of science, Phenomena that seemed impossible or paradoxical often pointed the way toward revolutionary new understanding. The exotic matter required for wormholes might seem like pure fantasy today, but it might also be the key to discoveries that transform our comprehension of space, time, energy, and the deepest structures of reality itself. Sometimes the most impossible requirements point toward the most profound truths, and sometimes the universe's greatest secrets are hidden behind barriers that seem insurmountable until someone finds an unexpected way around them. Here's where our cosmic detective story takes its most thrilling turn, where the universe reveals that its greatest secrets might be hiding in the most unlikely places imaginable. After decades of assuming that wormholes would be found near black holes, and after wrestling with the seemingly impossible requirements of exotic matter, scientists began to ask a revolutionary question. What if we've been looking in all the wrong places? What if the cosmos has been concealing its shortcuts, not in the dramatic, obvious locations, but in the quiet corners of reality where we least expect to find them? The answers to these questions are about to challenge everything you thought you knew about where cosmic phenomena can exist and thrive. Let's begin our journey through these unexpected locations with one of the most extreme and fascinating objects in our universe: neutron stars. These cosmic remnants are the collapsed cores of massive stars that have undergone supernova explosions, and they represent some of the most extreme conditions that physics allows. Imagine taking the entire mass of our sun and compressing it into a sphere only about 12 miles across. The result is matter so dense that a teaspoon of neutron star material would weigh as much as Mount Everest. The gravitational field at the surface of a neutron star is so intense that if you could somehow stand there, you would weigh about 100 billion times more than you do on Earth. But neutron stars aren't just remarkable for their incredible density. They're cosmic laboratories where the normal rules of physics are pushed to their absolute limits. The pressure inside a neutron star is so enormous that atomic nuclei are crushed together, creating exotic forms of matter that exist nowhere else in the known universe. Quarks, the fundamental particles that make up protons and neutrons, might be squeezed so tightly that they form strange new phases of matter with properties we can barely imagine. And it's precisely these extreme conditions that have caught the attention of wormhole researchers. The key insight is that neutron stars might naturally create the kinds of spacetime distortions necessary for wormhole formation, but without the destructive chaos that surrounds black holes. Unlike black holes, which hide their interiors behind impenetrable event horizons, neutron stars have surfaces that we can observe and study. More importantly, the extreme but stable conditions inside neutron stars might provide exactly the right environment for exotic matter to form naturally through quantum mechanical processes that we're only beginning to understand. Some theoretical physicists have proposed that the ultra-dense quark matter in neutron star cores might exhibit negative energy density under certain conditions, effectively creating pockets of naturally occurring exotic matter. If this is true, then neutron stars wouldn't just be cosmic lighthouses spinning in space. They would be cosmic wombs, continuously generating the very substance needed to create and maintain wormhole tunnels. The implications are staggering. There are an estimated 1 billion neutron stars in our galaxy alone, which means there could be a billion potential wormhole factories scattered throughout the Milky Way. But neutron stars aren't the only unexpected location where researchers have begun searching for cosmic shortcuts. Let's zoom out to the largest structures in the universe, the cosmic web. When astronomers map the distribution of galaxies across billions of light years, they discover something remarkable. Galaxies aren't scattered randomly through space. They're organized into an intricate network of filaments, walls, and voids that resembles a vast three-dimensional spiderweb stretching across the entire observable universe. These cosmic filaments are composed primarily of dark matter, that mysterious substance that makes up about 27% of the universe, but interacts so weakly with ordinary matter that we can barely detect it. The filaments can stretch for hundreds of millions of light years, containing more mass than millions of galaxies. Yet they're so diffuse that if you were traveling through one, you might not even notice. But here's where the story becomes truly extraordinary. Some researchers have proposed that these cosmic highways might literally be highways. Vast networks of interconnected wormholes that span the entire universe. The idea sounds like pure science fiction, but it's based on serious theoretical work. The cosmic web represents the largest scale structure in our universe, shaped by gravitational forces acting over billions of years. But what if gravity isn't the only force involved in creating these structures? What if the same processes that form the cosmic web also created conditions conducive to wormhole formation on truly cosmic scales? If microscopic wormholes in the quantum foam could somehow be stretched and stabilized by the dark matter in cosmic filaments, we might be looking at a transportation network that connects every galaxy in the observable universe. The implications of cosmic web wormholes are almost too vast to comprehend. If such a network exists, then the apparently empty space between galaxies might be filled with shortcuts that make intergalactic travel not just possible, but relatively straightforward for any civilization advanced enough to detect and navigate these cosmic highways. The dark matter that we struggle to understand might not just be invisible scaffolding holding the universe together. It might be the substrate for a cosmic internet connecting every corner of reality. But let's bring our focus back down to quantum scales, where some of the most revolutionary ideas about wormhole locations are emerging. Quantum entanglement, that spooky action at a distance that so troubled Einstein, has become one of the most experimentally verified phenomena in all of physics. When two particles become entangled, they remain mysteriously connected regardless of the distance separating them. Measure the properties of one particle, and you instantly know the properties of its entangled partner, even if it's on the other side of the galaxy. For decades, physicists treated quantum entanglement as a purely informational phenomenon, a correlation between particles that allowed for instant communication of measurement results but didn't involve any physical connection through space. But recent theoretical work has suggested something far more radical. What if quantum entanglement and wormholes are different manifestations of the same underlying phenomenon? What if every pair of entangled particles is connected by a microscopic wormhole that exists in dimensions we can't directly perceive? This idea, known as the ER equals EPR conjecture, named after Einstein-Rosen bridges and Einstein-Podolsky-Rosen entanglement, suggests that the quantum world might be held together by an invisible network of tiny wormholes. Every quantum interaction, every measurement, every entangled pair of particles might be mediated by these microscopic space-time tunnels. If this is true, then wormholes aren't rare cosmic curiosities. They're the fundamental architecture of reality itself, operating at every scale from the subatomic to the cosmic. The implications are mind-boggling. The quantum computer sitting in a laboratory, creating and manipulating entangled particles, might actually be creating and manipulating microscopic wormholes. The chemical bonds that hold molecules together, which depend on quantum mechanical interactions between electrons, might be sustained by tiny wormhole connections. The very stability of atoms themselves, governed by quantum mechanics, might rest on a foundation of space-time shortcuts so small and numerous that they form the hidden substrate of all physical reality. This quantum approach to wormholes also suggests unexpected locations where larger, more accessible wormholes might form. Regions of space where quantum entanglement is particularly strong or widespread might provide natural nucleation sites for wormhole growth. Laboratory environments where scientists create highly entangled quantum states might inadvertently be creating conditions conducive to microscopic wormhole formation. The boundary between quantum mechanics and general relativity, explored in experiments with quantum gravity effects, might reveal wormhole phenomena that we've been missing because we didn't know where to look. Another unexpected location for wormholes emerges from the study of phase transitions in the early universe. In the first fraction of a second after the Big Bang, the universe underwent a series of dramatic transformations as the fundamental forces of nature separated from their unified state. During these phase transitions, the fabric of space-time itself underwent radical restructuring, potentially creating exotic topological defects that persist to this day. Some of these defects, such as cosmic strings and domain walls, have been extensively studied by cosmologists, but other types of defects might create space-time geometries that support stable wormhole formation. If the early universe created a network of wormhole-generating defects, then these cosmic shortcuts might be distributed throughout space in patterns determined by the physics of the Big Bang itself. The universe might have been born with wormhole networks already built into its fundamental structure, hidden in the background geometry of space-time, and waiting for us to develop the technology to detect them. The search for wormholes in unexpected locations has also led researchers to consider the role of electromagnetic fields in space-time geometry. While gravity is by far the dominant force shaping the large-scale structure of the universe, extremely strong electromagnetic fields can also create measurable distortions in space-time. The magnetic fields around pulsars, rapidly rotating neutron stars, can reach intensities trillions of times stronger than Earth's magnetic field. Some theoretical work suggests that these extreme electromagnetic environments might create space-time geometries that support exotic matter formation and wormhole stability. If electromagnetic wormholes are possible, then they might be found around some of the most energetic objects in the universe: magnetars, quasars, and gamma-ray burst sources. These cosmic powerhouses generate electromagnetic fields so intense that they modify the quantum vacuum itself, potentially creating the exotic matter conditions necessary for wormhole formation. The high-energy phenomena that we observe from these objects, the intense radiation, the rapid variability, the violation of normal physical expectations, might be signatures of wormhole activity rather than conventional astrophysical processes. Perhaps most intriguingly, some researchers have suggested that wormholes might exist in the most mundane locations of all, in the seemingly empty space that surrounds us every day. The quantum vacuum, far from being truly empty, seethes with virtual particle pairs that constantly appear and disappear. The energy density fluctuations in this quantum foam might occasionally organize themselves into configurations that support temporary wormhole formation. These ephemeral tunnels would exist for incredibly brief periods and at unimaginably small scales, but they might be far more numerous than anyone has previously imagined. If vacuum wormholes are real, then every cubic centimeter of space around you contains thousands or millions of these microscopic shortcuts, constantly forming and dissolving in the quantum uncertainty that underlies all of reality. The air you breathe, the ground you walk on, the space between atoms in your own body, all of it might be permeated by a hidden network of wormhole connections that link every point in space to every other point through quantum tunnels in the fabric of space-time itself. The search for wormholes in unexpected locations represents more than just a shift in research strategy. It represents a fundamental change in how we think about the universe. Instead of viewing space-time as a mostly static stage on which cosmic drama unfolds, we're beginning to see it as a dynamic, living medium filled with hidden connections, secret passages, and invisible networks that span every scale from the quantum to the cosmic. The unexpected locations where wormholes might exist force us to reconsider our assumptions about what's normal and what's exotic in our universe. Perhaps the truly exotic phenomenon isn't the existence of wormholes, but their absence. Perhaps we live in a cosmos so thoroughly connected by space-time shortcuts that the real mystery isn't how wormholes form, but how we ever came to think of distant regions of space and time as truly separate from each other. As we prepare to explore the most mind-bending implications of wormhole existence, remember that the universe has consistently surprised us by hiding its greatest secrets in the places we least expect to find them. The cosmic shortcuts we seek might not be rare, dramatic phenomena confined to the neighborhoods of black holes, but common, subtle features of reality itself, woven so deeply into the fabric of existence that we've been looking through them rather than at them all along. Prepare yourself for what might be the most paradigm-shattering idea in the entire history of physics, a concept so revolutionary that it forces us to completely reimagine our place in the cosmos and our understanding of reality itself. Everything we've discussed so far, Einstein's bridges, black hole connections, exotic matter requirements, and unexpected locations, has been leading up to this moment, this revelation that will fundamentally change how you think about the space around you, the nature of existence, and the hidden architecture of the universe. What if wormholes aren't rare cosmic anomalies that we need to search for in the most extreme corners of the universe? What if they aren't exotic phenomena requiring impossible forms of matter and energy? What if, instead, wormholes are so common, so fundamental to the structure of reality, that they outnumber the stars in the sky by factors so vast that our minds can barely comprehend them? The revelation begins with a simple but profound question that emerged from the cutting-edge intersection of quantum mechanics and general relativity. What if space-time isn't the smooth, continuous fabric that Einstein envisioned, but rather something far stranger and far more connected? Recent theoretical developments in quantum gravity, the attempt to merge Einstein's theory with quantum mechanics, suggest that at the smallest possible scales of reality, space and time don't behave anything like our everyday experience suggests. Instead of a smooth geometric surface, space-time might be more like a foam, riddled with tiny holes, bubbles, and tunnels that connect distant regions of the universe in ways that completely bypass our normal understanding of distance and separation. This quantum foam exists at the Planck scale, distances so small that they make atoms look like galaxies. At this scale, roughly 10 to the negative 35th power meters, the very concept of smooth spacetime breaks down completely. The uncertainty principle of quantum mechanics ensures that energy and geometry fluctuate wildly, creating and destroying virtual particles and even virtual spacetime structures faster than light could travel across a proton. And it's here, in this seething quantum chaos that underlies all of reality, that some of the most brilliant physicists of our time believe wormholes might not just exist, but might be the dominant feature of spacetime's fundamental architecture. Imagine for a moment that you could zoom in on the fabric of spacetime with a microscope powerful enough to see individual units of geometry. Instead of finding smooth, continuous surface, you would discover something that resembles cosmic Swiss cheese, a foam-like structure where tiny wormholes appear and disappear trillions upon trillions of times per second. Each cubic centimeter of seemingly empty space would contain more wormhole connections than there are atoms in the observable universe. These quantum wormholes would be incredibly small and incredibly short-lived, lasting for time periods measured in units so brief that millions of them could form and dissolve in the time it takes light to travel the width of a proton. But here's where the revelation becomes truly mind-bending. What if these ephemeral quantum wormholes aren't isolated phenomena, but components of a vast interconnected network that spans the entire universe? What if every point in space is connected to every other point through multiple pathways in this quantum foam, creating a cosmic web of shortcuts that makes the entire universe fundamentally interconnected at the deepest level of reality? This would mean that the separation we perceive between objects, the distances we measure between stars and galaxies, the very concept of here and there, might be illusions created by our limited perspective on a reality that is actually seamlessly connected through invisible quantum tunnels. The mathematics supporting this revolutionary idea comes from some of the most advanced theoretical frameworks in modern physics. String theory, loop quantum gravity, and other approaches to quantum gravity all suggest that space-time has a discrete, granular structure at the Planck scale, rather than being infinitely divisible. But more importantly, they suggest that this granular structure might be topologically complex, filled with handles, tunnels, and connections that create shortcuts through the apparent geometry of spacetime. Consider the implications of what this means for our understanding of the universe. If quantum foam wormholes permeate all of space, then the vacuum around you right now isn't empty at all. It's one of the most densely connected regions imaginable. The space between your hand and this screen contains countless microscopic pathways that connect not just these nearby points, but potentially link to regions billions of light years away. The quantum vacuum that physicists once thought was the lowest energy state of empty space might actually be a bustling highway system of cosmic proportions, with information and quantum correlations flowing through wormhole networks at speeds that make light seem sluggish by comparison. This revelation also provides a potential solution to one of the deepest mysteries in quantum mechanics: the phenomenon of quantum entanglement. When two particles become entangled, they remain mysteriously correlated regardless of the distance between them, with measurements on one particle instantly affecting the properties of its distant partner. Einstein called this spooky action at a distance and was deeply troubled by its implications for our understanding of locality and causality. But if space is permeated by quantum wormholes, then quantum entanglement might not be action at a distance at all. It might be action through tiny space-time tunnels that make distant particles effectively adjacent to each other in the hidden dimensions of quantum foam. The ER equals EPR conjecture, proposed by physicists Juan Maldacena and Leonard Susskind, formalizes this connection between Einstein-Rosen bridges, wormholes, and Einstein-Podolsky-Rosen entanglement. According to this idea, every pair of entangled particles is connected by a microscopic wormhole that exists in dimensions beyond our normal three-dimensional space. The spooky action at a distance that so troubled Einstein would actually be communication through space-time shortcuts that make distant locations effectively touching each other in higher dimensional space. If this conjecture is correct, then the implications extend far beyond solving the mystery of quantum entanglement. It would mean that every quantum interaction, every chemical bond, every biological process that depends on quantum mechanics is mediated by microscopic wormhole connections. The DNA in your cells, held together by quantum mechanical forces, might be stabilized by tiny wormhole networks. The neural activity in your brain, which depends on quantum effects in microtubules and synapses, might be occurring through a web of quantum tunnels that connect different regions of your consciousness in ways that transcend normal space and time. But the revelation goes even deeper than individual quantum interactions. If quantum foam is permeated by wormhole networks, then these networks might serve as the fundamental communication system of the universe itself. Information about the state of quantum fields, the evolution of wave functions, and the outcomes of measurements might propagate through wormhole networks faster than light, creating a cosmic internet that operates below the threshold of our normal perception, but governs the behavior of reality at the deepest level. This hidden communication network might explain some of the most puzzling aspects of quantum mechanics, such as the apparent non-locality of quantum effects and the strange way that quantum systems seem to know about global properties of their environment. If every quantum system is connected to every other quantum system through microscopic wormholes, then the universe becomes a single, integrated quantum computer where information processing occurs through space-time shortcuts rather than through the slower mechanisms of electromagnetic radiation or particle propagation. The revelation also suggests a radically different picture of cosmic evolution and structure formation. If wormhole networks permeate space, then the early universe might have been even more densely connected than it is today, with quantum foam wormholes serving as conduits for information and energy transfer that shape the formation of the first structures. The cosmic microwave background radiation that we observe from the early universe might contain subtle signatures of wormhole activity, encoded in temperature fluctuations and polarization patterns that we haven't yet learned to recognize. As the universe expanded and cooled, the quantum foam networks might have undergone phase transitions that changed their topology and connectivity. Some wormholes might have grown larger and more stable, while others collapsed or became too small to carry significant amounts of information or energy. The dark matter and dark energy that dominate our current universe might be manifestations of these evolving wormhole networks, with dark energy representing the expansion-driving effects of quantum foam connectivity, and dark matter representing the gravitational signatures of stable wormhole structures. This perspective on wormholes as fundamental features of quantum foam also opens up entirely new possibilities for technology and exploration. If microscopic wormholes are everywhere, then the challenge isn't creating them from scratch or finding rare naturally occurring examples. The challenge is learning to detect, access, and manipulate the wormhole networks that already surround us. Advanced civilizations might develop quantum technologies that can identify stable pathways through the foam, amplify microscopic wormholes to macroscopic sizes, or create artificial quantum states that generate new wormhole connections on demand. The revelation forces us to confront the possibility that faster-than-light travel isn't just theoretically possible. It might be happening constantly all around us at the quantum level. Every quantum measurement, every collapse of a wave function, every instance of quantum decoherence might involve information traveling through wormhole shortcuts that bypass the normal speed of light limitations. The universe might be naturally equipped with a transportation and communication system far more advanced than anything we've imagined, operating continuously at scales so small that we've been completely unaware of its existence. But perhaps the most profound aspect of this revelation is what it suggests about the nature of consciousness and our place in the cosmos. If our brains operate through quantum effects mediated by microscopic wormholes, then consciousness itself might be a fundamentally non-local phenomenon. Your thoughts and memories might be distributed across quantum foam networks that span regions far larger than your physical brain. The boundary between self and universe might be far more porous than we've ever imagined, with consciousness emerging from quantum connectivity patterns that transcend normal space and time. This could explain some of the deepest mysteries about consciousness: how subjective experience arises from objective matter, how memories are stored and retrieved, how creative insights seem to emerge from nowhere. If consciousness operates through quantum wormhole networks, then the mind might have access to information and computational resources distributed throughout space-time, drawing on quantum correlations and connectivity patterns that span the cosmos. The revelation that wormholes might be ubiquitous features of quantum foam doesn't just change our understanding of physics. It changes our understanding of everything. It suggests that we live in a universe far stranger, far more connected, and far more alive than we ever dared to imagine. The empty space between atoms, between stars, between galaxies isn't empty at all. It's filled with invisible highways carrying information, energy, and perhaps even consciousness itself through shortcuts that make every point in the universe potentially adjacent to every other point. As we prepare to explore the implications of this revelation for our future as a species and our understanding of cosmic possibilities, remember that we're not just talking about abstract physics or distant theoretical scenarios. If quantum foam wormholes are real, then they're operating right now, right here, mediating every quantum interaction in your body and connecting you to the deepest structures of reality in ways that are only beginning to be understood. The universe might not just be stranger than we imagine. It might be stranger than we can imagine. And we might be far more integrated into its hidden architecture than we ever suspected. The mind-blowing revelation isn't just that wormholes might exist. It's that they might be so fundamental to reality that asking whether they exist is like asking whether space and time exist. They might not be features of the universe. They might be the universe, operating at every scale from the quantum to the cosmic, creating the hidden connectivity that makes existence itself possible. Now, we arrive at perhaps the most staggering part of our journey, exploring what it would actually mean for humanity, for science, for the very nature of existence itself, if wormholes truly permeate the fabric of reality as we've just described. The implications are so vast, so fundamentally transformative, that they challenge every assumption we've ever made about space, time, causality, and our place in the cosmic order. We're not just talking about new transportation methods or communication technologies. We're talking about a complete revolution in how we understand the nature of reality, consciousness, and the ultimate structure of the universe itself. Prepare yourself for ideas that will stretch your imagination to its absolute limits and beyond. Let's begin with the most immediately obvious implication. If wormhole networks truly permeate space-time at the quantum level, then faster-than-light travel isn't just possible. It's been happening constantly, everywhere, since the beginning of time. But we're not talking about building starships that break the light barrier in the traditional sense. Instead, we're talking about learning to navigate and manipulate the hidden highway system that nature has already built into the very structure of reality. Imagine developing technology that could identify stable pathways through the quantum foam, expand microscopic wormholes to macroscopic sizes, or create artificial quantum states that open doorways through space-time itself. The technological implications are almost incomprehensible. If we could learn to detect and access quantum foam wormholes, we might be able to step from Earth to the center of the Milky Way galaxy in less time than it takes to walk across a room. The 26,000 light years that separate us from our galaxy's core would become irrelevant, no more significant than the distance between floors in a building connected by an elevator. The vast cosmos, with its billions of galaxies separated by unimaginable distances, would shrink to the size of a neighborhood where every location is instantly accessible to anyone with the right quantum key. But the implications go far beyond simple transportation. If information can travel through quantum wormhole networks faster than light, then we're looking at communication technologies that would make our current internet seem like smoke signals. Imagine being able to send messages instantaneously to any point in the universe, receiving data from civilizations in distant galaxies in real time, or accessing information stored in quantum networks that span the entire cosmic web. The limitations imposed by the speed of light, which currently make interstellar communication a game of patience measured in years or decades, would become as obsolete as the limitations once imposed by the speed of horses. The implications for space exploration are equally revolutionary. Instead of building massive rockets that take months or years to reach nearby planets, we might develop quantum navigation systems that could transport entire research teams to the outer edge of the solar system, to distant star systems, or even to other galaxies in time frames measured in minutes or seconds. The hostile vacuum of space, the deadly radiation of interplanetary travel, the enormous energy requirements of conventional propulsion, all of these barriers would become irrelevant if we could simply step through quantum doorways that bypass normal space-time entirely. But let's think even bigger than individual transportation or communication. If wormhole networks truly permeate reality, then they might provide access to computational resources distributed throughout the universe. Quantum computers operating through wormhole connections could tap into processing power spread across cosmic scales, solving problems that would require more matter and energy than exists in our entire observable universe if tackled through conventional means. We might be able to simulate entire universes, model the behavior of galactic clusters, or solve mathematical problems that are currently beyond the reach of any conceivable technology. The implications for energy generation are equally staggering. If microscopic wormholes connect every region of space to every other region, then we might be able to tap into energy sources distributed throughout the cosmos. Imagine being able to harvest energy from the cores of distant stars, from the accretion disks around black holes, or from the quantum fluctuations of space-time itself. The energy crisis that currently constrains human civilization would become a historical curiosity, replaced by access to power sources that dwarf anything available through conventional means. But perhaps even more profound are the implications for our understanding of time itself. If wormholes can connect different regions of space, could they also connect different moments in time? The mathematics of general relativity suggests that under certain conditions, wormholes might create closed time-like curves, pathways through space-time that loop back on themselves, potentially enabling travel to the past or future. If quantum foam wormholes operate outside our normal temporal constraints, then the very concept of past, present, and future might be far more fluid than we've ever imagined. The implications of time travel through wormhole networks are both fascinating and terrifying. On one hand, we might be able to observe historical events directly, study the formation of galaxies and stars in real time, or even communicate with past and future versions of ourselves and our civilization. On the other hand, time travel creates logical paradoxes that could undermine the very consistency of reality. If the past can be changed, if causality can be violated, if effects can precede their causes, then the orderly, predictable universe that science has spent centuries mapping might be revealed as a far stranger and more dangerous place than we ever suspected. The implications for biology and medicine are equally revolutionary. If quantum effects in living systems are mediated by microscopic wormholes, then life itself might be a phenomenon that operates through space-time shortcuts. The quantum coherence effects observed in photosynthesis, bird navigation, and possibly even consciousness might be examples of biological systems that have evolved to exploit wormhole networks for enhanced efficiency and capability. Understanding and harnessing these effects could lead to medical treatments that operate at the quantum level, healing techniques that work through space-time manipulation, or even life extension technologies that tap into the fundamental connectivity of the universe. The implications for consciousness and the nature of mind are perhaps the most profound of all. If our brains operate through quantum effects mediated by wormholes, then consciousness itself might be a non-local phenomenon distributed across space-time networks that span regions far larger than our physical bodies. This could explain some of the deepest mysteries about the mind: how subjective experience arises from objective matter, how memories are stored and retrieved across decades, how creative insights seem to emerge from connections that transcend normal cognitive processing, and how consciousness maintains its continuity despite the constant replacement of atoms and molecules in our brains. If consciousness operates through wormhole networks, then the boundary between individual minds might be far more porous than we've ever imagined. Telepathic communication, shared memories, collective intelligence, and even forms of group consciousness might be natural consequences of quantum connectivity rather than supernatural phenomena. Advanced civilizations might develop technologies that enhance these natural quantum connections, creating forms of collective intelligence that span entire species or even multiple species distributed across galactic scales. The implications for our search for extraterrestrial intelligence are equally transformative. If wormhole networks permeate space, then advanced civilizations might be using quantum shortcuts for communication and travel that completely bypass the electromagnetic signals we've been searching for through projects like SETI. We might be looking for civilizations that communicate through radio waves when they're actually talking through quantum foam networks that operate below our current threshold of detection. The galaxy might be bustling with activity and communication that we're completely missing because we're listening to the wrong channels. More intriguingly, if wormhole networks truly connect all regions of space and time, then contact with extraterrestrial civilizations might not require finding them in our local cosmic neighborhood. We might be able to communicate with intelligences that exist in distant galaxies, in different eras of cosmic history, or even in parallel universes connected to ours through quantum foam bridges. The search for extraterrestrial intelligence might become a search for the quantum keys needed to access the cosmic communication networks that already connect all conscious beings throughout space and time. The implications for cosmology and our understanding of the universe itself are equally revolutionary. If wormhole networks have existed since the beginning of time, then they might have played a crucial role in cosmic evolution, structure formation, and the development of complexity. The cosmic web of dark matter that connects galaxies across billions of light years might be more than just gravitational scaffolding. It might be a manifestation of wormhole networks that have shaped the universe from its earliest moments. The apparent fine-tuning of physical constants that makes life possible in our universe might be explained by quantum connectivity rather than cosmic coincidence. If all regions of spacetime are connected through wormhole networks, then information about successful configurations for matter, energy, and physical law might propagate through these networks, leading to the emergence of life-supporting conditions wherever the network connectivity is sufficiently complex and stable. But perhaps the most profound implication of all is what wormhole-permeated reality would mean for the ultimate nature of existence itself. If every point in space and time is connected to every other point through quantum shortcuts, then the universe becomes not a collection of separate objects and events, but a single, integrated system where separation is an illusion created by our limited perspective. The boundaries between self and other, between here and there, between past and future, might be artificial constructs that dissolve when viewed from the perspective of quantum foam connectivity. This could mean that consciousness, intelligence, and perhaps even individual identity are far more distributed and interconnected than we've ever imagined. You might not be an isolated mind trapped in a physical body, but a pattern of quantum connectivity that extends throughout space-time networks, sharing information and experience with other conscious entities across cosmic scales. Death might not be the end of consciousness, but simply a reconfiguration of quantum network connections, and birth might not be the beginning of awareness, but the focusing of distributed consciousness into a particular space-time pattern. The implications challenge our most basic assumptions about reality, identity, consciousness, and the nature of existence itself. If wormholes truly permeate the fabric of space-time, then we're not just living in a universe with hidden shortcuts. We're living in a universe that is fundamentally interconnected at every level, where the apparent separation between objects, minds, and moments is revealed as the greatest illusion of all. As we prepare to explore how humanity might detect, study, and ultimately harness these cosmic networks, remember that we're not just talking about new technologies or scientific discoveries. We're talking about the potential for a transformation in human consciousness and capability so profound that it would make the difference between Stone Age hunters and modern civilization seem trivial by comparison. The implications of wormhole-permeated reality don't just change what we can do. They change what we are, what we mean, and what it means to exist in this strange, wonderful, and deeply connected cosmos we call home. Here we stand at one of the most exciting frontiers in the history of science, the moment when theoretical speculation meets cutting-edge technology, when abstract mathematics collides with real-world experimentation, and when humanity's greatest mystery hunters turn their attention to finding evidence for phenomena that could revolutionize our understanding of reality itself. The search for wormholes has evolved from pure speculation to serious scientific investigation, employing some of the most sophisticated technologies ever created and pushing the boundaries of what's possible in experimental physics. What makes this search particularly thrilling is that we're not just looking for new particles or distant objects. We're hunting for the hidden architecture of space-time itself, for cosmic shortcuts that might be operating right under our noses. The modern wormhole search represents a fascinating convergence of multiple scientific disciplines, each contributing unique tools and perspectives to the hunt. Gravitational wave astronomy, quantum computing, particle physics, and even information theory are all playing crucial roles in developing new ways to detect phenomena that exist at the intersection of quantum mechanics and general relativity. What's particularly remarkable about this multi-pronged approach is that it's revealing how interconnected different areas of physics really are. The same quantum foam that might harbor microscopic wormholes also affects gravitational wave propagation, influences particle interactions in high-energy accelerators, and shapes the behavior of quantum information systems. Let's start with one of the most promising avenues of investigation: gravitational wave detection. The historic detection of gravitational waves by the LIGO Observatory in 2015 opened up an entirely new window into the universe, allowing us to observe phenomena that were previously invisible to all forms of electromagnetic astronomy. These ripples in space-time itself, created by the collision of black holes and neutron stars, provide direct evidence that Einstein's vision of dynamic, malleable space-time geometry is absolutely correct. But for wormhole hunters, gravitational waves offer something even more exciting: a potential method for detecting the space-time distortions that wormholes would create. When a wormhole forms, whether naturally or artificially, it would create distinctive signatures in the gravitational wave spectrum that differ from the patterns produced by colliding black holes or neutron stars. The exotic matter required to stabilize a wormhole would generate gravitational effects unlike anything produced by ordinary matter, creating wave patterns that trained physicists could potentially recognize as the smoking gun evidence for space-time tunnels. More intriguingly, if microscopic wormholes in the quantum foam occasionally grow large enough to influence space-time geometry on detectable scales, they might, produce subtle but characteristic distortions in gravitational waves passing through regions of space with high wormhole density. The next generation of gravitational wave detectors, including space-based observatories like the Laser Interferometer Space Antenna, will be sensitive enough to detect gravitational waves from much smaller and more distant sources than current ground-based detectors. These enhanced capabilities might finally provide the sensitivity needed to detect the subtle gravitational signatures of wormhole activity, whether from individual large-scale wormholes or from the collective effects of dense networks of microscopic quantum foam tunnels. Particle physics is providing another crucial avenue for wormhole detection through high-energy accelerator experiments that probe the fundamental structure of space-time at the smallest possible scales. The Large Hadron Collider, which discovered the Higgs boson by smashing protons together at energies approaching the conditions that existed moments after the Big Bang, is also searching for evidence of extra dimensions, microscopic black holes, and other exotic phenomena that might reveal the hidden architecture of reality. Some theoretical models suggest that high-energy particle collisions might occasionally create microscopic wormholes that would leave distinctive signatures in the debris patterns of particles produced by these cosmic energy impacts. The search for particle-scale wormholes requires incredibly sophisticated detection techniques because these quantum tunnels would exist for such brief periods and at such tiny scales that they would be nearly impossible to observe directly. Instead, physicists look for indirect evidence, unusual energy distributions, unexpected particle correlations, or violations of conservation laws that might indicate that some energy or information has taken a shortcut through a microscopic wormhole rather than traveling through normal space-time. The challenge is distinguishing genuine wormhole signatures from the countless other exotic phenomena that become possible at the energy scales where quantum mechanics and general relativity begin to merge. Perhaps even more exciting is the emerging field of quantum wormhole detection through quantum computing and quantum information theory. If the ER equals EPR conjecture is correct, if quantum entanglement and microscopic wormholes are the same phenomenon, then every quantum computer and quantum communication system might already be creating and utilizing wormhole connections without us realizing it. The race is now on to develop quantum technologies sophisticated enough to detect and characterize these potential wormhole networks operating within quantum information systems. Quantum computers that manipulate entangled particles might be inadvertently opening and closing microscopic wormholes with every quantum operation. Researchers are developing experimental protocols that could distinguish between conventional quantum entanglement effects and genuine wormhole-mediated connections by looking for subtle differences in how information propagates through quantum systems. These experiments push the boundaries of quantum technology while potentially revealing whether the quantum world is held together by space-time shortcuts that operate below our current threshold of detection. The search for naturally occurring wormholes in space is employing some of the most advanced astronomical technologies ever developed. Radio telescopes, X-ray observatories, and gamma-ray detectors are all being used to search for the distinctive signatures that wormholes would produce if they exist in significant numbers throughout the galaxy. Fast radio bursts, those mysterious, intense flashes of radio waves from distant galaxies, are being scrutinized for patterns that might indicate wormhole activity rather than conventional astrophysical phenomena. More intriguingly, astronomers are beginning to search for gravitational lensing effects that might be produced by wormhole networks rather than by ordinary matter. If space is permeated by microscopic wormholes, they might create subtle but detectable distortions in light passing through regions with high wormhole density. These effects would be incredibly difficult to distinguish from the lensing produced by dark matter, but advanced statistical analysis techniques might eventually reveal patterns in cosmic light distortion that point to wormhole activity rather than conventional gravitational effects. The search is also extending into cosmology, where researchers are looking for evidence that wormhole networks played a role in the early universe's evolution and structure formation. The cosmic microwave background radiation, that ancient light from when the universe first became transparent, might contain subtle patterns that reveal the influence of primordial wormhole networks on the development of cosmic structure. These patterns would be incredibly faint and would require the most sophisticated data analysis techniques to extract from the noise, but they might provide the first direct evidence that wormholes have been shaping cosmic evolution since the earliest moments after the Big Bang. Laboratory experiments are pushing the boundaries of what's possible in controlled wormhole research. While we're nowhere near creating macroscopic wormholes in laboratory conditions, researchers are developing experiments that could detect the effects of quantum foam wormholes on electromagnetic fields, particle interactions, and space-time geometry itself. The Casimir effect, which demonstrates that the quantum vacuum can exhibit exotic properties similar to those required for wormhole formation, is being studied with unprecedented precision to determine whether these vacuum effects might occasionally organize themselves into wormhole-like configurations. Some of the most ambitious laboratory experiments are attempting to create conditions where the boundary between quantum mechanics and general relativity becomes accessible to direct observation. By manipulating electromagnetic fields, gravitational fields, and quantum states simultaneously, researchers hope to create environments where microscopic wormholes might form spontaneously, or where existing quantum foam wormholes might be amplified to detectable scales. These experiments represent some of the most challenging technical achievements in the history of physics, requiring control over matter and energy at levels that approach the theoretical limits of what's physically possible. The search for wormholes is also being aided by advances in theoretical physics and computational modeling that help researchers know what to look for and where to look for it. Sophisticated computer simulations of quantum foam structure are revealing the kinds of patterns and signatures that wormhole networks might produce, providing roadmaps for experimental searches. Artificial intelligence and machine learning algorithms are being trained to recognize potential wormhole signatures in vast data sets from gravitational wave detectors, particle accelerators, and astronomical observations, automating the search for phenomena that might be too subtle or rare for human researchers to identify manually. Perhaps most remarkably, the search for wormholes is beginning to reveal connections between phenomena that were previously thought to be completely unrelated. The same mathematical frameworks used to study black holes are providing insights into quantum computing. The techniques developed for gravitational wave detection are finding applications in quantum information theory. The statistical methods used to analyze cosmic microwave background patterns are being applied to particle accelerator data. This cross-pollination of ideas and techniques is not just accelerating the wormhole search. It's revealing the deep unity underlying all of physics. The international collaboration required for wormhole detection is bringing together researchers from dozens of countries and hundreds of institutions, creating a global network of scientists who share data, techniques, and insights in real time. This collaborative approach is essential because wormhole detection requires combining observations from multiple types of detectors, theoretical insights from various areas of physics, and computational resources distributed across continents. The search for cosmic shortcuts is itself creating new forms of scientific connectivity that span the globe. But perhaps the most intriguing aspect of the ongoing search is that we might already have detected wormhole activity without recognizing it for what it is. The quantum correlations that enable quantum computing, the dark energy that drives cosmic expansion, the fast radio bursts that puzzle astronomers, the apparent fine-tuning of physical constants. Any or all of these phenomena might be manifestations of wormhole networks operating at scales or in ways that we haven't yet learned to recognize. As detection technologies become more sensitive and theoretical understanding becomes more sophisticated, we're approaching a threshold where genuine wormhole detection might transition from possibility to reality. The next decade could see the first confirmed detection of microscopic wormholes in laboratory experiments, the first gravitational wave signatures of large-scale wormhole activity, or the first astronomical observations that can only be explained by space-time shortcuts operating on cosmic scales. The search continues not just in laboratories and observatories, but in the imaginations and calculations of theoretical physicists who are constantly pushing the boundaries of what might be possible. Every new insight into quantum gravity, every advancement in gravitational wave detection, every breakthrough in quantum computing brings us closer to answering the ultimate question. Are we living in a universe where space-time shortcuts are rare curiosities, or are we swimming in an ocean of cosmic connectivity that we're only beginning to perceive? The hunt for wormholes represents more than just another scientific investigation. It's humanity's attempt to discover whether we're truly alone in vast empty spaces, or whether we're already connected to every corner of the cosmos through invisible networks that operate at the deepest level of reality itself. We've traveled together through the most mind-bending territory in all of physics, from Einstein's revolutionary bridges through space-time to the possibility that our universe is riddled with invisible shortcuts at every scale imaginable. We've explored black holes and quantum foam, exotic matter and cosmic webs, gravitational waves and quantum computers. But now we arrive at the moment of truth, the convergence point, where all of our exploration leads to a single, universe-defining question that will determine not just our understanding of cosmic phenomena, but our comprehension of the very nature of existence itself. The ultimate question isn't simply whether wormholes exist beyond black holes. It's whether we're ready to live in a universe where the fundamental assumptions about space, time, separation, and connectivity that have guided human thought for millennia might be completely wrong. The question that emerges from our journey is more profound than whether we can build faster-than-light spaceships or communicate instantaneously across galactic distances. It's more significant than whether we can harness exotic matter or navigate through quantum foam networks. The ultimate question is this: are we prepared to discover that the universe we thought we knew, a cosmos of vast empty spaces punctuated by isolated islands of matter and energy, is actually a seamlessly interconnected web where every point is potentially adjacent to every other point through pathways that operate outside our normal understanding of distance and time? Consider what this question really means for humanity as a species. For our entire history, we've built our civilizations, our philosophies, our sense of identity around the assumption that we are fundamentally separate beings living on isolated worlds scattered throughout an incomprehensibly vast and largely empty universe. The distances between stars have seemed so immense, the barriers to communication and travel so insurmountable, that we've developed deep psychological and cultural patterns based on isolation, scarcity, and the fundamental loneliness of consciousness in an indifferent cosmos. But what if all of these assumptions are wrong? What if the apparent separation between individuals, between worlds, between galaxies is an illusion created by our limited perception of a reality that operates through connectivity patterns we've never learned to see? The ultimate question forces us to confront the possibility that loneliness might be a temporary condition created by our current inability to access the communication networks that already connect all conscious beings throughout space and time. The implications go far beyond technology or scientific understanding. They challenge our most basic concepts of what it means to be human, what it means to be alive, and what it means to exist as conscious entities in a universe that might be far more alive and aware than we've ever imagined. If wormhole networks truly permeate reality, then consciousness itself might be a distributed phenomenon that operates through space-time shortcuts, making individual identity and collective awareness different aspects of the same underlying cosmic process. But the ultimate question also carries within it a profound responsibility. If we discover that wormhole networks exist, that space-time is riddled with shortcuts, that faster than light travel and communication are not just possible, but natural features of reality, then we'll be faced with choices that will determine the future of our species and possibly the fate of consciousness throughout the universe. How do we use technologies that could instantly transport us anywhere in the cosmos? How do we handle communication systems that could connect us with civilizations separated by billions of years of cosmic evolution? How do we maintain our humanity while gaining access to capabilities that approach the godlike? The discovery of accessible wormhole networks would place humanity at a crossroads unlike any we've faced in our history. We would need to decide whether to use these cosmic highways for expansion and exploration, or whether to focus on deepening our understanding of the consciousness and connectivity that such networks might reveal. We would need to choose between becoming a spacefaring civilization that spreads throughout the galaxy, or becoming a transcendent species that learns to operate through the hidden dimensions of reality itself. The ultimate question also forces us to confront the possibility that we're not the first species to face these choices. If wormhole networks have existed throughout cosmic history, then advanced civilizations might have been using them for millions or billions of years. The apparent silence of the cosmos, the famous Fermi paradox that asks where all the extraterrestrial civilizations are hiding, might be explained not by the rarity of life or intelligence, but by the fact that truly advanced species have learned to operate through quantum foam networks that are completely invisible to our current detection methods. We might be living in a galaxy that's bustling with activity and communication, surrounded by civilizations so advanced that they've transcended physical space-time entirely, operating through wormhole networks that make their activities as invisible to us as radio waves are to a species that has only learned to communicate through smoke signals. The ultimate question becomes whether we're ready to discover that we've never been alone, that consciousness and intelligence might be common throughout the universe, but operating through channels we've never learned to access. But the ultimate question isn't just about what we might discover. It's about what discovering wormhole networks would do to our understanding of causality, free will, and the nature of choice itself. If information can travel through quantum shortcuts that operate outside normal space-time, then the boundary between past, present, and future might be far more fluid than we've ever imagined. The decisions we make today might influence events in the past, while future choices might already be shaping the present through wormhole connections that bypass linear time. This raises profound questions about the nature of consciousness, responsibility, and moral action. If our minds operate through quantum networks that span space and time, if our thoughts and decisions ripple through wormhole connections to influence events throughout cosmic history, then individual consciousness might be far more significant and far more connected to the universal order than we've ever suspected. The ultimate question becomes whether we're ready to discover that consciousness itself might be the fundamental force that shapes reality through its interactions with the hidden architecture of space-time. The question also challenges our scientific methodology and our understanding of what constitutes proof or evidence. Wormhole networks operating at quantum scales might be so subtle, so deeply integrated into the fabric of reality, that they're nearly impossible to detect directly. Instead, we might need to infer their existence from patterns that emerge across multiple scales and multiple types of phenomena: quantum correlations, gravitational anomalies, consciousness studies, and cosmological observations that only make sense when viewed as manifestations of underlying connectivity. This would require a new form of science that integrates insights from physics, neuroscience, information theory, and even consciousness research into a unified framework for understanding reality as a connected whole rather than a collection of separate parts. The ultimate question becomes whether we're ready to abandon the reductionist approach that has dominated science for centuries in favor of a more holistic understanding that treats connectivity and relationship as fundamental features of reality. But perhaps the most challenging aspect of the ultimate question is what it reveals about the nature of knowledge itself. If wormhole networks connect all regions of space and time, if quantum foam creates pathways for information transfer that operate faster than light, then the distinction between knowledge and reality, between information and physical substance, between thought and existence, might be far more blurred than we've ever imagined. Consciousness might not be something that observes reality from the outside, but something that participates in reality's creation through its interactions with quantum networks that span the cosmos. The ultimate question becomes whether we're ready to discover that the boundary between mind and universe, between observer and observed, between consciousness and cosmos, might be artificial distinctions that dissolve when viewed from the perspective of wormhole-mediated connectivity. The implications extend to our understanding of identity, mortality, and the meaning of individual existence. If consciousness operates through distributed quantum networks, if information about our thoughts and memories can propagate through space-time shortcuts, if individual identity is maintained through patterns of connectivity rather than through localized brain activity, then death might not be the end of consciousness, but simply a reconfiguration of network connections. The ultimate question becomes whether we're ready to discover that individual existence might be far more durable and far more connected to cosmic processes than we've ever believed. But the ultimate question also carries within it a note of profound humility. If wormhole networks truly permeate reality, if space-time is far stranger and more connected than we've imagined, then we're forced to acknowledge that our current understanding represents only the smallest glimpse of a reality so vast and complex that it might be forever beyond complete comprehension. The ultimate question becomes whether we're ready to live with the profound mystery of existence while continuing to explore and discover without expecting to ever achieve complete understanding. This humility extends to our relationship with other potential forms of consciousness and intelligence throughout the universe. If wormhole networks have enabled the evolution of species and civilizations with capabilities that transcend our current imagination, then our first contact with truly advanced intelligence might come not through radio signals or physical encounters, but through our growing ability to access the quantum communication networks that such civilizations might have been using for eons. The ultimate question becomes whether we're ready to discover that intelligence and consciousness might be far more common throughout the universe than we've imagined, but operating at levels of sophistication and through channels of connectivity that make our current technological capabilities seem primitive by comparison. Are we prepared to be the youngest and least advanced participants in a cosmic community that has been operating through wormhole networks since long before our planet was formed? As we stand at this crossroads between our current understanding and the revolutionary possibilities that wormhole research might reveal, the ultimate question isn't really about wormholes at all. It's about whether we're ready to grow beyond our current limitations as a species, to embrace forms of existence and consciousness that transcend our historical experience, and to take our place in a universe that might be far stranger, far more alive, and far more interconnected than we ever dared to dream. The answer to whether wormholes exist beyond black holes might ultimately be less important than whether we're prepared for the consequences of that answer. Are we ready for a universe where separation is an illusion, where consciousness spans cosmic scales, where the boundaries between self and cosmos dissolve into patterns of connectivity that operate through the hidden architecture of reality itself? The ultimate question isn't whether we can find wormholes. It's whether we can handle what finding them might reveal about the true nature of existence in this strange, wonderful, and mysteriously connected cosmos we call home. So here we are, standing at the edge of one of the most profound questions humanity has ever faced. We've journeyed together from Einstein's first glimpse of cosmic bridges to the mind-bending possibility that you, right now, as you're watching this, might be surrounded by invisible highways connecting every corner of the universe. We've explored ideas so revolutionary that they challenge everything we thought we knew about space, time, and the very nature of reality itself. But this isn't just another fascinating scientific story that we can file away and forget about. This is about you. This is about us. This is about the possibility that we're living in a universe so much stranger, so much more connected, so much more alive than we ever imagined. Every breath you take, every thought you think, every quantum interaction happening in your body right now might be part of a cosmic network that spans the entire universe. Think about that for a moment. Really think about it. You might not be an isolated consciousness trapped on a tiny rock in the vast emptiness of space. You might be an integral part of a cosmic web of consciousness and connection that operates through shortcuts we're only beginning to understand. The loneliness that sometimes grips us when we look at the night sky, that sense of being small and insignificant in an indifferent universe. What if that's all been wrong? What if we've never been alone? What if we've always been connected to something infinitely larger and more wonderful than we could have imagined? This is why I created the Lazy Cosmos. Not to overwhelm you with complicated equations or intimidate you with academic jargon, but to share with you the sheer wonder and mind-blowing beauty of the universe we're discovering together. Every time we explore these cosmic mysteries, we're not just learning about distant phenomena. We're learning about ourselves, about our place in this strange and wonderful reality, about the incredible journey that consciousness itself is taking through space and time. But here's the thing. This journey isn't something that happens to us passively. We're active participants in this cosmic exploration. Every time you engage with these ideas, every time you let your imagination stretch to encompass possibilities that seem impossible, every time you look at the world around you and wonder about the hidden connections that might be operating beneath the surface, you're contributing to humanity's greatest adventure. Your curiosity matters. Your questions matter. Your sense of wonder matters. Because if wormholes do exist, if the universe really is this interconnected web of cosmic highways, then it's going to be human curiosity, human imagination, human determination to understand the impossible that finally reveals these hidden truths. It's going to be people like you, people who aren't satisfied with simple answers, people who are brave enough to consider ideas that stretch the boundaries of what seems possible. So what do you think? Are you ready to be part of this cosmic detective story? Are you ready to explore a universe that might be far stranger and more wonderful than anything science fiction has ever imagined? Because I promise you, we're just getting started. The cosmos has so many more secrets to share, so many more mind-bending mysteries to explore together. If this journey through wormholes and hidden cosmic highways has sparked something inside you, if it's made you look at the space around you differently, if it's made you wonder about the true nature of reality, if it's given you even a glimpse of the incredible adventure that consciousness is having in this universe, then hit that like button. Let me know that these ideas matter to you, that these explorations are worth continuing. And subscribe to the Lazy Cosmos, because we're going to keep pushing the boundaries of the possible together. We're going to explore ideas that challenge everything you thought you knew about reality. We're going to dive into mysteries so profound that they change not just what you know, but who you are. Because that's what the universe does. It transforms us, challenges us, inspires us to become something greater than we ever imagined we could be. Drop a comment and tell me, what blew your mind the most in this exploration? Was it the possibility that wormholes might be everywhere around us? The idea that consciousness itself might operate through cosmic networks? The realization that we might be living in a universe where separation is just an illusion? I want to hear your thoughts, your questions, your own theories about how reality might work at its deepest levels. And if there's a cosmic mystery you want us to explore next, whether it's the nature of time travel, the possibility of parallel universes, the mystery of consciousness itself, or any other mind-bending question about our strange and wonderful cosmos, let me know in the comments, because this is our journey together, and I want to explore the questions that fascinate you, that keep you awake at night, wondering about the incredible universe we're part of. Remember, you're not just a passive observer watching the cosmos from the outside. You're an active participant in the greatest story ever told. The story of consciousness discovering itself, of intelligence exploring its own cosmic home, of wonder and curiosity pushing against the boundaries of the possible until they reveal new truths about the nature of existence itself. The universe is calling to you, inviting you to be part of this cosmic adventure. The only question is, are you ready to answer? Until next time, keep looking up, keep wondering, and keep exploring the lazy cosmos together. Because the greatest discoveries in the universe are still waiting for us to find them.